Okay, so this is the solution to the problem minimum window substring. It's labeled hard and I'm going to discuss the official solution for this problem. So you're given two strings S and T, and S is the string you will be working on as your primary source and T assume is the target string. Now you're given a certain condition saying that there are some characters in T, which could be also duplicates, but there are some characters in T and you have to ensure that you find a substring in S such that it contains all of the characters in T. Now this substring is not just any substring, but the minimum window substring, the minimum length substring. Okay, so this problem essentially asks you to solve two problems. First is of enumerating all of the possible substrings, and the naive solution says it could be done in order of n square time. There's a small problem though. The m and n could be 10 to the power 5, which means that we're looking at something not of the order n square, but maybe n log n or n, or something even better. Okay, what's the second problem it wants us to solve? Once you have enumerated the possible valid sort of these windows or substrings, we want to find the minimum possible length of such string. Okay, these are the two problems we'll keep at the back of our mind. Now let's discuss the logic of this problem. First is the observation that the ordering of T does not matter. The only thing that they ask you to do is for any substring, which is going to be a valid string, you have to just ensure that every character in T, including duplicates, is included in the window. What it essentially means is that inside of T, you have certain characters A's, B's, and C's, and you can sort of compress them and say, this is the amount of A's in it, this is the amount of B's in it, this is the amount of C's in it. The ordering of these three does not matter within themselves, but their values, the keys and the values, both do. And you can just take this dictionary and compare it to the string given to you. This brings me to the second point. Since we are talking already about the T in terms of a dictionary, let's also look at windows or strings in terms of dictionaries. At any given point of time, we'll have this window and we won't look at the window anymore, but we'll look at the dictionary that the window has. The dictionary of whatever character it has and their values. This will help us easily compare with the values in the dictionaries in the dictionary of T. We'll actually do that right now. The goal is to find a string, a substring in S, which has the dictionary of T. And this is how we'll set it. Then the window is going to be what? It's again a dictionary, and we have the setup as keys as characters and the values as the frequency of these characters. Again, this means that the ordering does not matter, and this is what we want. So we'll create a default date of int. Okay. Now let's talk about the third observation. Now the question says that it's minimum window substring, but why include the word window at all? You just need substrings, right? The window word itself gives you the hint of thinking about it like a sliding window problem. You can have two indices L and R, and both of these can point to different variables. Between now L and R, you'll have this particular window. Left is the left part of the window, right is the right part of the window. Both of these pointers can move around the string and thus define a particular window we're looking at. Let's write that down too. So we'll start L and R from both 0. And our goal is to continue this while R is less than the length of S. That's because as soon as right sort of moves out of bounds, we'll just end the game right. Okay. And each point of time, I want to do R plus equals to 1. This is trivially fine. Okay. What now? At every point of time, what do I want to do? L is here and R is trying to move here, 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 and here. This will help us enumerate the proper substrings we want. Of course, the issue of this minimum is something we're going to solve in a second, but first, R is going to be increasing by 1 each time while L remains the constant here. At every point of time, you want to now include the new character inside of the window dictionary. So we'll have the window dictionary here and we'll access the S of R and we'll just do plus equals to 1. As simple as that. Now let's talk about the minimum part of these. What if this dictionary goal is the same as the dictionary window? I'm basically saying that in the current window of L to R, we have found this sort of goal inside of it. And that's great news, right? What do we also want to do here? We also want to look at how we can sort of reduce its length. See, at any given point of time, we're moving R. So R is sort of defining the end position. Maybe we can also reduce the strings over here. Maybe we can also remove these and the answer is just from here to here. This means that we have found the minimum possible answer as well. So let's also do it. So while goal is equal to window, go ahead and increase the L by 1. And each time you do, we'll do the opposite of what we did here. We'll just say from this window, remove S, L, and we'll do minus equals to. If they are still the same, just keep on going and keep on reducing these characters till you find the minimum possible length. At this point, we'll also store the minimum possible length. Let's say it's from 0 to infinity. It's the default case. And once we're done with this loop, we'll say answer equals to the minimum possible distance between L and R. We'll find that by saying, okay, we have L and R here. Sorry. And we'll have the key as what? We want the minimum possible length between any L and any R, which means that the difference between them is the length of the string. So we'll have a lambda function here saying the item and taking the input as item and returning the item of 1 minus the item of 0. Now the initialization of 0 comma infinity should make more sense. Okay. Now what's remaining to do is just return this thing and we'll be done. So we'll return the answer. It's not the answer now. We need to access the string of the answer of 0 to answer of 1. Now we can only do that in the case we've found a valid substring. What if we haven't? There are cases, as they mentioned here, as A and AA, which has the empty string as the answer. In case none of this loop is able to give us the answer, we'll just return empty string if answer is still the same as what we started with originally. What did we start with originally as? 0 comma infinity. And this is it for the solution, right? Looks pretty good, makes a lot of sense. If you look at it, however, these 2 points are not exactly correct in any manner. We don't actually care about the goal being the same as the window. Goal is what we aim for, window is the current window in our focus. Equality is no longer making any sense. It may be longer than the goal, The window may be longer than the goal. In case like this, where B, A, and C was the answer, the length of the window was 4 and the length of the goal was just 3. So equality is kind of off. We need a better way to compare these dictionaries. Of course, we're getting closer and closer to the answer. And what we can do is, instead of comparing these dictionaries, we can just take their lengths and compare that. So we'll have the required length. We'll say required and formed, starting with the length of goal. And formed is the current length of the window, but it's not just the length of the window anymore. It's also representing how many valid characters have been accessed in the window, which are the same as the goal. Basically, formed says inside of goal we have a certain amount of characters, and for each of them characters we're going to increase the count by 1 in the value formed if we have it in the window. Okay, if that sounds a bit complicated, let me just write it simply here. and it'll make a lot of sense. Okay, what do we want here? We want, hey, is this current value is f of r, s of r inside of goal? If that value is inside of goal, which is what we're aiming for, and the current window has as many of these s of r's as the goal has. What I'm basically saying is not only have I found the right character, but I found it in the right amount. And as soon as I've done that, I can have found plus equals to 1. Now the condition here is no longer goal equals to window. We'll instead check required with formed. So required formed. If required is the same as formed, which means that we have found the valid window. While now the valid window exists, keep on removing these values from the left hand side. And so we'll just do the opposite of what we saw here. Instead of just decreasing this window size, we want to say if the current character happens to be important and inside of goal, then I would want to check also if it happens to be inside of goal and the window length of this guy is no longer the same as or equal to the goal of SRR. In that case, form minus equals to 1. Okay, now this should make more sense, the logic of dictionary comparison. Because earlier it wasn't making any sense, but now we're just comparing both of their lengths. The lengths of what? The lengths of valid characters. Okay, let's do a quick sanity check. Okay. Cool, I'll take a, oh no wait, this is SFL. I was going to say I'm going to take a debugging break, but let's hope I don't need that. Cool, there's one more problem now. While you're doing this, you're increasing L by 1 each time. But you will reach a point where increasing L by 1 did not make any more sense. The while loop will terminate after that L plus 1 has been done and it's now over. So you'll actually want to reduce the L by 1 again. So we'll just do this here. And this should be it. Let's hope that should is. Cool, we'll submit this and we'll be done with this. So again, enumerating was one big issue that this problem wanted us to solve. There could be n squared total valid substrings, but we wanted a better way to enumerate them. And we did that by windows. We also wanted to find the minimum possible of those. And so while we had those windows bounded by L and R, L are always increasing, we found the minimum by also decreasing the L at the same time, or also increasing the L by the same time, decreasing the window size. And then we applied the ordering of T logic to make it a dictionary. We also made the original window a dictionary and then compared both of these dictionaries together. This itself was an issue and we solved it by instead taking the lengths of their dictionaries. Cool. Feel free to go over this code again or my write-up if you want any more sort of info or ideas. Discussions are most welcome. Anyways, this is it for the solution of minimum window substring.